Assalamualaikum and a very good day to my lecturer, Dr. Abdul Halim. My name is Qurratu Aina binti Muhammad Noor and today I will be presenting the technical review presentation regarding the residual static corrections. Without further ado, let's proceed to the first part, which is the standard SEISMIC data processing flow. As you can see in this flow, static correction is applied after the data sorting and before the stacking. Now let's proceed to the introduction of the residual static corrections. Residual static corrections is designed to correct small inaccuracy in the near surface model. Next, it is also the relative time changes between traces that tend to smoothly align the wavelets of seismic reflections events. Besides, it is able to resolve the short wavelength content of the travel time distortions, but the estimation of the long wavelength trend is limited by the spread length of the recording cable, which is the spread length. This is mentioned by the Wiggins et al. In 1976. Lastly, almost all the residual statics method required the seismic data to be normal move-out corrected. As Tanner et al. 1974 mentions, there are reasons for analyzing residual statics on NMO-corrected data. One of them is that the travel time delays caused by the wavelength velocities and source reservoir offsets are generally much larger than travel time deviations caused by the other factors such as the residual static anomalies. So, the differences between the general statics and residual statics are: general statics is applied in the early stage of processing. Meanwhile, residual statics is generally applied in the later stage in processing. Secondly, general statics is the correction applied for topography and influence from weathered layer. Meanwhile, residual statics is the normally implement after general statics were applied. Besides, general statics is the solve this problem only for a certain part. Meanwhile, in residual statics, it is the measure trace delays by cross correlations. General statics need small shift corrections for certain area or regions. Residual statics need compute surface consistent static shifts from trace delays. The general statics is advantage of correcting long period statics. Meanwhile, the advantage of residual static is to correct short period statics. Now, let's proceed to the application of residual static corrections. The paper is Residual Static Corrections by means of CRS attributes by I. Kong Lin and E. Wick. So, the introductions. Onshore datasets are particularly interested in the residual static adjustment. They are utilized to reduce the weathering layer's influence on reflections, travel times, as well as the redatuming method faults. After residual static correction, the result of stacking approaches should indicate an improved signal-to-noise SN ratio. Common Reflection Surface (CRS) is considered to be used because it provides additional information about the subsurface by the CRS attributes. Here, the CRS attributes serve as a basis for the move-out correction, which is important for determining the residual statics. The theoretical background introduced to the residual static corrections problem, and the first result of the synthetic test show that the new approach is able to estimate residual static adequately. So now let's proceed to the problem statement. So the problem statement is that by using field static adjustment, the topography effect on reflections time is greatly reduced. However, the reduction time distortion persists due to fast changes in elevations and near surface velocity or thickness of the weathering layer. To eliminate these remains which the field static corrections did not compensate, the residual static correction assigns every shots and every receiver an additional static time shift. The time shift of residual static corrections aim to enhance the continuity of reflections events and to improve the signal-to-noise ratio after stacking. Zhang and Habrel 2002 have introduced the topography into the CRS stack method, which can be seen as a kind of field static corrections. But so far, the 2D ZO CRS stack method does not yet account for residual static corrections. Thus, a new approach of residual static correction based on the CRS attributes is presented in the following. Now let's proceed to the method and processing. Firstly, conventional residual static correction methods. Residual static correction approaches must give one exclusive time shift for each source and receiver, corresponding to one common source or common receiver, gather respectively, to achieve surface unconformity. The crucial conventional residual static corrections technique is to apply and approximate NMO corrections. Then, the reflections event in each gather are considered to be misaligned due to the source static, a receiver static, and residual move out. Secondly, new approach by means of CRS attributes. The CRS stack method provides additional section 1 for each CRS attributes. These attributes are alpha, RNIP, Rn are parameters of stacking surface given by the equation below. With the ZO traveling time TO, the near surface velocity VO, the emergence angle alpha of the ZO ray, the radius of the curvature of the NIP wavefront RNIP measured at XO, and the radius of curvature of the normal wavefront Rn, also measured at the XO. This stacking surface from the CRS stack method improve the SN ratio even more than the NMO or DMO or stack method. New approach is based on the cross correlations and is similar to the technique of Ronen and Claerbout 1985. This very first step is to perform at least the initial 2D ZOCRS. Each trace of the stimulated ZO section will serve as a pilot trace for the necessary cross-correlation. So now, let's proceed to the third method, which is the CRS move-out correction. To correct for the CRS move-out, the half offset H and midpoint X dependency from previous equation has to be eliminated. Moreover, the common reflection surface can be transformed into a horizontal plane at the time TO by subtracting the move-out given by the equation below, where TO is given by the considered time sample of the simulated ZO sections. This resulted in the pre-stacked traces are multiply contained in the CRS supergathers but with different move-out corrections. So now let's proceed to the next method, which is the cross-correlations. The difference to the supertrace cross-correlation method of Ronen and Claerbout 1985 is that the cross-correlation are not performed between the supertraces but as correlations of every single move-out corrected trace with the pilot trace. All correlation results that belong to the same source or receiver location will be summed up. It will be resulted in the residual static value that is given by the time associated with the maximum of the sum correlation results. Lastly, iterations. The pre-stacked traces are time shifted with the associated total time shift after the residual static values are derived from the cross-correlation results. Each pre-stacked traces total time shift is simply the sum of the associated source and receiver static values. If the CRS stack of these corrected pre-stacked traces is not yet satisfactory, the entire procedure can be started again in the two different ways. One way is to perform the CRS search and all other steps as in the first iterations. The other way is to assume that the CRS attributes found in the first iterations are the true attributes and therefore the CRS search is omitted. So now let's proceed to the result and discussions. As you can see here, A is the original synthetic data set, B with random residual statics, and C is the CRS move out corrected CRS supergather for CMP 120. Simulated ZO section of the optimized 2D ZO CRS stack from A and B. The CMP within the CRS aperture are shown one after the other and their traces are consecutively numbered. It is obvious that the move-out correction did not correct the random residual statics. The reflections events are more or less flattened. It is shown in the figure C. Next, the result is from A is the obtained source residual static and B is the obtained receiver residual static. Residual static values at the random statics are displayed as solid line. The dashed line represents the peak residual statics after 10 CRS supergather has contributed to the correlation sum, and the dotted lines represented the peak residual static after 4 CRS supergather have contributed to the correlation sum. So as for next result, A is the CMP gather without residual static, B with the random residual static, and C is with the residual static corrections. The result above shows the CMP 120 with residual static correction move enhancement following the first iteration of novel technique. The CRS stack's spatial aperture consider more traces than just those collecting within CMP collects. The first synthetic test revealed that this innovative approach can improve the simulated ZO sections of the datasets that have been affected by the residual static. So now, let's proceed to the major advances and discoveries. The technique is the equivalent offset mapping. Firstly, the principle of equivalent offset and common scatter point collections, which were introduced for pre-stack time migrations, are used in the equivalent offset mapping (EOM map) approach of the residual static analysis. Secondly, without NMO correction or the typical move-out assumptions, and without good stacking velocities informations, the EO map static approach can use reliable residual static estimates that are velocity independent and are usually required just one iterations. Thirdly, for seismic data collected in the places with simple subsurface structures, the EO map can approach estimate residual static with comparable accuracy to conventional static methods. Lastly, the advancement of this technique is that compared to the depth migration approach given by Tejan et al. 1994 and Lerner 1998, the EO map method is not only substantially faster but also less velocity sensitive. In practice, the EO map approach can be made more efficient by selecting the right parameters. So now let's proceed to the current debate and future directions. So the current debate is, firstly, in most circumstances, the EO map does not require velocity informations. Secondly, conventional approaches are frequently ineffective when dealing with data with a complicated structure since their hyperbolic normal move-out assumption is no longer true. Lastly, because of the EO map as a partial migration and its inverse are less impacted by the reflecting structure, the EO map statics approach does not produce long wavelength static accuracy, which is the long wavelength. So for the future direction of the research, it's possible that the current implementation of the EO map technique hasn't been optimized. Thus, the implementation of EO map technique need to be applied more in the research, such as enhancement of some algorithm in the areas of equivalent offset mapping migrations and surface consistent static decomposition statics. In conclusion. So, firstly, the conclusion is residual static correction is designed to correct small inaccuracy in the near surface model. Secondly, after residual static corrections, the result of stacking approaches should indicate an improved signal-to-noise SN ratio. Thirdly, residual static correction may have limitations that can affect certain results as there is a method approach such as included CRS attributes to improve the result that affected by the residual static. Lastly, there is technique that could yield the reliable residual static corrections without NMO correction or the typical move-out assumption, which is applying the EO map technique. That's all from me. Thank you.